Welcome back to 6th grade science. So far, we've covered our introduction to energy, and then the last video we touched on the energy types in a little bit more depth, and then we got into energy conversion. Today we're going to take a step back and look at thermal energy and more specifically heat in association to thermal energy. For the next couple days, we're going to cover thermal energy in its different capacities. Thermal energy is the energy of moving particles within matter. More specifically, it is the total amount of kinetic energy, or the energy of the moving particles within matter. Remember that all matter has thermal energy because the particles in that matter are always moving. It doesn't matter if that matter is a solid, a liquid, or a gas. The particles are always moving, just at different rates. What are some factors that affect thermal energy? When you think the word thermal, what's the first thought that pops in your head? For me, my head immediately thinks heat, temperature. And temperature is something that affects thermal energy. Thermal energy is the total amount of kinetic energy in matter, whereas temperature is the average amount of kinetic energy within that matter. Another factor that affects thermal energy is mass, and we haven't really talked about mass yet. We'll get into that a little bit later, but for right now, all you need to understand is that mass is the amount of matter in an object. Mass and temperature are things that both affect the amount of thermal energy that an object has, or that some type of matter has. In my hand here, I have a very large ice cube. We're going to say it's another 1,000 grams, which realistically would be a lot bigger, but I only have so much room on my screen. Here, let's see if I can make it bigger for you. Yeah, see, that's a little big, so I'm going to shrink it back down just for the example. That's better. All right, so I have my 1,000 gram ice cube in this hand, and I have a steaming cup of coffee in this hand. So there's more of this, but it's cold. And I only have a little bit of this, but it's hot. So which one has more thermal energy? Well, if you remember from the last video and my spiel about 5 seconds ago, the ice cube has more thermal energy. And the reason being is because it's bigger. Because thermal energy is the total amount of movement of particles within that matter. So to provide another example, I have these two glass jars, which might be a little difficult for you to see, so I'm going to step forward. So in this jar, I have paper clips, quite a few of them. And in this jar, I have it filled almost to the top with water. Which of these do you think has greater thermal energy? Did you pick this one? If you did, it's not quite right. The one with water has greater thermal energy. Right now the water is a little bit colder than room temperature because I used the cold side of the tap, but this has more thermal energy because there's more to it than this paper clip, or rather these paper clips. So remember, thermal energy is more than just temperature. Thermal energy is the amount of the matter and the amount of particles that are moving within that matter. So the greater amount of matter you have, the greater thermal energy. Now, if I had an equal amount of boiling water and cold water, the boiling water would have greater thermal energy because the temperature is higher and it's the same amount mass-wise. So you got to take into effect both components. In summary for that, more mass equals more particles, which equals a larger total amount of kinetic energy, which equals more thermal energy. Temperature is the average of kinetic energy of particles in matter. The more the particles move all over the place, the more kinetic energy there is, and the higher the temperature is, which also means that it feels warmer. The less particles move, the less kinetic energy there is, and the lower the temperature, which means that it's colder. In a previous video, I talked about the different units associated with temperature. So you have degrees Fahrenheit, which we use in the United States, you have degrees Celsius, which other countries use, and then you have Kelvin. And Kelvin are the SI unit for temperature. I'm going to change screens really quick, and then I'm going to show you guys a little bit on how to convert degrees from Fahrenheit to Celsius, Celsius to Fahrenheit, or Celsius to Kelvin, Kelvin to Celsius. Technically, you can go Fahrenheit to Kelvin as well, but that's a couple steps. So I'm just going to show you the main 3 base level steps. All right, guys, so now we're going to get in some conversion. So go from degrees Fahrenheit to degrees Celsius. We're going to take our degrees Fahrenheit, subtract 32 degrees, and then divide that entire number by 1.8, which will tell us the degrees Fahrenheit in degrees Celsius. So I'm going to give you an example. For easy math, let's do 32 degrees Fahrenheit. We're going to subtract 32 from that, and then divide everything by 1.8 to give us our degrees Celsius. So 32 minus 32 is, yep, you're right, it's 0. So we have 0 divided by 1.8 equals degrees Celsius. For this example, 0 divided by anything is 0. All right, so we have 0 degrees Celsius, which is equal to 32 degrees Fahrenheit. This is what we ended with, and this is what we started with. That's how we know they're equal. Next, we're going to go from degrees Celsius to degrees Fahrenheit. So last time we took degrees Fahrenheit, subtracted 32, and then divided by 1.8. What we're going to do this time is kind of the opposite. So we're going to take our degrees Celsius, we're going to multiply it by 1.8, and then we're going to add 32 to that overall to get our degrees Fahrenheit. So for this example, and again with easy math, I'm going to do 1 degree Celsius times 1.8 plus 32 to get our degrees Fahrenheit. So 1 times 1.8 is, yep, 1.8 plus 32 equals degrees Fahrenheit. So 1.8 plus 3.2 equals 33.8 degrees Fahrenheit, which is equal to 1 degree Celsius. And I know this because this is what we got in the end, and this is what we started with. Next, we're going to do degrees Kelvin to degrees Celsius. And this is your degrees Kelvin minus 273 is your degrees Celsius. So if I have 275 degrees Kelvin, subtract 273, that's going to give me my degrees Celsius, which is 2 degrees Celsius is equal to 275 Kelvin. This is what I ended with it, my result, and this is what I started with. And finally, for today, we're going to go from degrees Celsius to Kelvin, which, opposite of what we just did, we're going to take our degrees Celsius, add 273 to it to get our Kelvin. So for our degrees Celsius here, we're going to use 20 degrees Celsius plus 273 to figure out our Kelvin. 20 degrees plus 273 is 293 Kelvin, which is equal to 20 degrees Celsius, because this is what my end result is, and this is what I started with. All right, now we are back from learning about converting, and I feel like it's getting a little warm in here. I don't know about you guys, but I think this lava pit behind me is a little warm. Remember how I've mentioned that the warmer the particles, or the warmer the substance, the more the particles move around. So as they're moving around and they are coming into contact with a colder substance, they are running into the particles of that substance. And every time they hit, they're transferring a little bit of their thermal energy to the colder item. So over time, it's going to get to what's known as equilibrium, where the temperatures and the amount of thermal energy are equal. Many of you probably like your drinks to be cold. So if you have soda sitting out on the counter and you want to cool it down, you'll pour it into a cup and then put some ice in it. And you probably think that the ice is cooling down the soda. And that's only kind of true. What's happening is the warmer particles of the soda are bouncing into the cold particles of the ice. And so the soda is slowly losing its thermal energy from these collisions. So the ice isn't cooling down the soda, rather the soda is heating up the ice, which then causes the ice to melt until you get a nice cold drink because the temperatures are balancing out. The amount of thermal energy is balancing out. Specific heat is the measure of how much energy is required to raise the temperature of a substance. Specifically, specific heat is the amount of energy in joules required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Specific heat is given to different types of matter because each type of matter has a different specific heat. The higher the specific heat, the more energy it takes to raise the temperature. So something like iron, which has a lower specific heat, when compared to water, which has a higher specific heat, the iron takes less time than the water to heat it up. That's all I have for today, but we're going to spend a few days talking about thermal energy, so it's not the last you've heard of it. Please remember that if you have any questions to reach out to your teacher, whether that's Miss Cameron or myself. Bye!